Betelgeuse, a colossal red supergiant star located in the Orion constellation, has long fascinated astronomers and stargazers alike. Its staggering size is difficult to comprehend. If placed where our Sun resides, it would extend beyond the orbit of Jupiter, dominating the inner solar system with its sheer enormity. Perched on Orion's shoulder, Betelgeuse has become not only a symbol of the vastness of the cosmos but also an object of intense scientific study due to its unique properties. Unlike most stars, Betelgeuse exhibits considerable instability with dramatic fluctuations in brightness that have sparked speculation about its potential to explode as a supernova. These fluctuations have been particularly pronounced in recent years, capturing both scientific and public attention. The James Webb Space Telescope has recorded a remarkable 250% surge in its luminosity, a change that is highly unusual for a red supergiant and indicative of processes occurring deep within the star. Social media updates have also chronicled a 142% increase in brightness, with subsequent observations showing further spikes, emphasizing that Betelgeuse has become one of the most closely watched stars in the night sky. These events have propelled it to become the seventh brightest star visible from Earth, further cementing its status as a celestial object of extraordinary interest. The potential explosion of Betelgeuse offers astronomers a rare opportunity to study the life cycle of massive stars in detail. Classified as a semi-regular variable star, Betelgeuse brightness changes periodically, reflecting internal processes that are otherwise invisible to observers. Since 2019, the star has exhibited increasingly erratic behavior following the expulsion of a significant portion of its outer atmosphere in an event referred to as the Great Dimming. This phenomenon caused unprecedented fluctuations in both brightness and radial velocity, prompting speculation about the star's imminent demise. Despite these dramatic signs, predicting exactly when Betelgeuse might explode remains an extraordinary challenge. Stellar evolution is an inherently complex process, and the timeline of events leading to a supernova depends on multiple internal factors, many of which are not directly observable. Currently, Betelgeuse is undergoing fusion processes in its core, burning elements such as helium, carbon, oxygen, and silicon. This progression will eventually lead to the fusion of iron, a stage where energy production ceases and the core can no longer support the star's immense weight. At that point, the core is expected to collapse, potentially triggering a supernova that could leave behind a neutron star or a black hole. Historical observations suggest that Betelgeuse has been changing gradually over millennia, indicating that while its current instability is notable, the final stages of its life may still be centuries away. Nevertheless, the star's present behavior provides a unique window into the late stages of stellar evolution, allowing scientists to observe processes that are typically inferred rather than seen directly. The fusion of heavier elements within the core, moving from carbon to oxygen and magnesium, represents a transition toward the eventual core collapse. Depending on the rate of these processes, Betelgeuse could experience a supernova within decades, or it might remain in this transitional phase for tens of thousands of years. This unpredictability underscores the intricate and variable nature of stellar evolution, where even the most sophisticated models must account for a wide range of possible outcomes. If the star were to explode within our lifetimes, it would be an unprecedented spectacle. The initial signs of the explosion would likely include a surge in neutrinos and high-energy photons, signaling the release of immense energy from the star's core. Within days, the star would dramatically brighten, potentially rivaling the luminosity of the full moon and casting shadows at night. Over the following weeks, its brilliance could dominate the sky, and the after effects would linger for months, providing an extraordinary opportunity to study the physics of supernova remnants in unparalleled detail. Even if Betelgeuse does not explode imminently, its current oscillations and irregular brightness patterns continue to captivate astronomers. Observations of these fluctuations offer critical insights into the dynamics of massive stars and the processes that govern their lifetimes. Each new measurement refines models of stellar behavior, shedding light on the mechanisms that drive instability and mass loss in red supergiants. The expulsion of outer layers, as seen during the Great Dimming, allows scientists to study how massive stars shed material and prepare for eventual collapse, a process that is essential to understanding not only stellar evolution but also the enrichment of the cosmos. Supernovae play a crucial role in the cosmic ecosystem by dispersing heavy elements into space, seeding the formation of new stars, planets, and ultimately the building blocks of life. Betelgeuse, therefore, is not only a subject of curiosity, but also a key player in the broader narrative of cosmic evolution, illustrating how the death of one star contributes to the creation of new systems across the universe. Advances in observational technology have significantly enhanced our understanding of Betelgeuse. Instruments such as the James Webb Space Telescope allow astronomers to monitor its brightness fluctuations in real time, providing data that were previously inaccessible. These observations have revealed complex and often unpredictable behavior, including shifts in luminosity and spectral characteristics that challenge conventional models. By studying these changes, scientists gain insight into the mechanisms of mass loss, the internal dynamics of stellar cores, and the stages leading up to core collapse. These findings are not limited to Betelgeuse alone. They inform our understanding of other red supergiants and massive stars approaching the end of their lifetimes. The data gathered from Betelgeuse can refine models of how supernovae occur, the distribution of energy and matter during such explosions, and the role of massive stars in shaping the interstellar medium. The anticipation of Betelgeuse eventual supernova has captured the imagination of both the scientific community and the public. Unlike most cosmic phenomena, a supernova of this magnitude would be visible to the naked eye, potentially even during daylight, dominating the night sky for weeks. Beyond the visual spectacle, such an event would allow astronomers to study the physics of core collapse directly, observing neutrinos and high-energy photons released from the star's core. The expanding shock wave and debris cloud would provide a detailed laboratory for examining the interactions between stellar material and the surrounding space. While Betelgeuse is relatively close at approximately 600 light-years away, this distance ensures that any explosion poses no threat to Earth, allowing us to witness the event safely. Interestingly, observing Betelgeuse is akin to looking back in time. The light we see today left the star more than 6 centuries ago, meaning any cataclysmic events that may have occurred since are still traveling toward us. It is conceivable, though unlikely, that Betelgeuse has already exploded and we are simply awaiting the arrival of that light. This temporal delay serves as a humbling reminder of the vast scales of time and distance that define universe. As supernova events such as the unexpected explosion of a massive blue star in 1987 demonstrate the surprises inherent in stellar evolution. These rare occurrences have historically challenged prevailing theories and emphasize the importance of continuous observation. Similarly, Betelgeuse's recent erratic behavior provides an unparalleled opportunity to refine our understanding of the late stages of massive star life cycles. By examining its rapid oscillations, erratic brightness, and mass loss events, astronomers can better model the processes leading to core collapse and eventual supernova. New observation contributes to a deeper comprehension of how massive stars live and die, revealing the extraordinary forces at work within them. Betelgeuse exemplifies the balance between fragility and resilience in stellar life, offering insight into the complex interplay of nuclear fusion, gravity, and mass loss that defines the evolution of red supergiants. The Great Dimming event of 2019 marked a pivotal moment in the study of Betelgeuse. The star expelled a significant portion of its outer atmosphere, leading to unprecedented fluctuations in luminosity and spectral properties. These changes provided a rare chance to examine the mechanisms by which massive stars lose mass, an essential process in preparing for eventual supernova collapse. Understanding these processes has far-reaching implications for astrophysics, including insights into how supernovae enriched the interstellar medium with heavy elements crucial for the formation of planets and life. Each stage of Betelgeuse evolution contributes to the larger cosmic cycle, demonstrating the interconnectedness of stars and the universe they inhabit. Observing the star in its current state allows scientists to capture a detailed snapshot of a red supergiant approaching the end of its life, offering lessons that extend beyond a single stellar object. Modern astronomical instruments have enabled real-time observation of Betelgeuse fluctuations, a feat previously unattainable due to technological limitations. These observations have revealed highly complex behavior, including irregular cycles of brightness that deviate from the star's historical patterns. Such data are invaluable for refining theoretical models, providing empirical evidence that informs predictions of stellar behavior across different masses and evolutionary stages. By monitoring Betelgeuse, astronomers can study the life cycles of massive stars in unprecedented detail, enhancing our understanding of the processes that shape galaxies and the cosmos as a whole. The star's erratic luminosity, spectral shifts, and mass ejections offer a comprehensive case study in the mechanics of stellar evolution, from fusion in the core to the eventual dispersal of matter into space. During a supernova, Betelgeuse eventual supernova will provide an extraordinary opportunity to study one of the universe's most energetic events directly. When the core collapses, the resulting explosion will release neutrinos and high-energy photons that can be detected on Earth, offering insight into the internal processes of the star. The expanding shock wave and ejected material will illuminate surrounding space, providing an unparalleled laboratory for observing the physics of supernovae. While such an event is unpredictable in its exact timing, even its potential has already reshaped our understanding of massive stars, emphasizing the importance of continuous monitoring and observation. Each fluctuation in Betelgeuse's Brightness offers a piece of the puzzle, revealing the intricate dynamics of nuclear fusion, gravitational forces, and energy transfer that define the life and death of massive stars. The study of Betelgeuse also underscores the role of massive stars in the cosmic recycling process. Supernovae distribute elements, such as carbon, oxygen, and heavier metals into the interstellar medium, enriching it for the formation of new stars and planetary systems. Betelgeuse, in its final stages, exemplifies this process, serving as a direct contributor to the cosmic ecosystem. Its instability and eventual demise are not merely isolated events but part of the broader narrative of stellar evolution, chemical enrichment, and the formation of life-supporting environments. Observation, therefore, contributes to both fundamental astrophysics and our understanding of how the universe continually regenerates itself. Even without a supernova, Betelgeuse continues to provide a wealth of information. Its current erratic behavior, rapid oscillations, and changing luminosity serve as a natural laboratory for studying massive stars. By tracking these changes, astronomers can test and refine